Okay, so that's
put in a symbol out and see if that
Always have to be prepared. Okay, before we get on with the festivities, I want to actually talk about the existence and uniqueness theorem for first orders. These are, well, not in general, but the nonlinear ones for these are kind of sketchy. There's of course, the linear case. So it says the initial value problem. Y prime plus Gt 1 equals Gt, where y naught is y naught, and is the initial condition, has a unique solution on any interval I. So that's this where E and G are continuous.
what does IVP stand for?
Huh?
What does the value problem?
Oh, okay. Initial value problem. Right. So it's a differential equation with an initial condition given. That is a first order linear. As long as our coefficients are continuous, we can actually find a solution. The proof here is actually not that bad. It's actually very computational. The proof is actually the integrating factor method. So we know that y equals the integral of is going to be mu times g as a constant all over mu. Gives the solution. And because all our functions are continuous, mu itself is an exponential. We can integrate a continuous function. The answer might not be nice. We might not be able to express it in elementary functions. However, on some interval, we'd be able to approximate that integral to any desired degree of accuracy. So that's actually not so bad. The nonlinear case is a little bit more careful though. So this is if you have a general y prime equals f of t y. This problem has a unique solution on the rectangle described by all t values between a and b. So that's our independent variable. There will be a range on which the independent variable will give the solution, as well as that, provided one, f itself needs to be continuous. and 2, and now this is a word condition. This is typically the condition given, even though there's another condition that could work in this place. The partial derivative of f with respect to y is also continuous. Just mentioned, instead of the partial f with respect to y is continuous condition, we may have something that's easier to obtain. F of ty is what we call Lipschitz continuous. That is, there exists a positive k such that the difference in t1 y minus t. The difference between those two y values will always be less than or equal to a constant times the difference in the t values for all t values. This is called Lipschitz continuity. You'll never see it again, probably never hear of it again until you're a math major doing real analysis. So I probably wouldn't worry about it. So, as long as our f is continuous and the partial with respect to y is continuous, it turns out that this will have a unique solution. Now, the proof outline for this is a very cumbersome proof outline. Basically, you assume y equals some function that you should call phi of t solves the ODE. And you start with a guess phi of 1 of t. Usually they start with a guess of 0. And they do this kind of Newton-Raphson-ish approximation method where they successively generate new phis. And then you have phi of 2, that's going to be the integral of f of t, phi of 1. So they're replacing the y with this function, which at first we assume it's 0. And then for phi of 3, you're going to compute this integral, assuming it can be computed. And you're going to plug that answer back. And of course, there are going to be limits here, and that's going to be a ds, but whatever. And you're pretty much going to keep doing this. You're going to generate each new function by integrating the function, the original function when you plug in the previous guess. And it turns out and after doing that,
you are not being very solid. That's what
and it turns out in sequence, phi 1, phi 2, phi n, and you just continue, it will converge. It will converge to a solution. This is called the Picard's iteration method. And it's not at all obvious why this would work. So your textbook actually goes through many things where it explains how do we know this converges to something? How do we know that thing is going to solve the original equation? How do we know that there are a lot of things that go into it, but if you have the continuity in these two, it turns out all those things are going to work out. By doing this repeated method here, this iteration method, called the Picard's iteration method, you can actually converge to a solution. So there's not much I'll say about the proof because it's teaching now a bunch of real analysis instead of linear algebra. That's just going to take too much time.
Professor,
Yes?
this Lipschitz continuous just mean it can be differentiated twice?
No, it means exactly the expression that which I think I missed. It means specifically that inequality.
But is it like something that's differentiable also continuous?
Yes, but Lipschitz continuous and continuous is not the same thing. They're different. Remember, continuous just means the limit as you approach the point equals the value of the function at the point. Differentiable means the derivative limit exists. Lipschitz continuous means that particular inequality holds. I can find a k value so that holds. Let's consider some examples. It's more instructive at this point to look at some examples here. And I might look at some more next time. I don't want to spend too much time on this right now. Where I look, maybe I'll look a little bit at the geometry of things, but right now let's keep things computational. Let's actually do, where we're going to solve some after making a prediction. So here's an example. It's nonlinear. Of course, it's computational, so I'm going to make it an easy one. Let's say we look at this function, this ODE. We have y of 3 equals 3. Now, question. Are we guaranteed a unique solution on some interval? Containing 3. Should say some rectangle, I should say. So I need to be continuous around the x equals 3 and the y equals 3. So around the point 3, 3, there should be a region around that point where a unique solution would exist. Outside of that region, we don't know anything, but can I actually guarantee myself a solution in this situation?
No.
Why not?
It's not continuous.
What's not continuous?
When you plug in y equals 3, if you didn't have initial conditions, it would be equal to 0.
Okay, 0 is not a problem. Zero is not a problem. Plug in something, you get 0, doesn't make it discontinuous.
What if we have like y equals 2.9, and then you get a negative in the radical?
It's a cube root. It's a cube root. So we can have negatives on the cube root. Cube root is going to be defined for all real numbers in general. So the answer here is no. Now, why is the answer no? It turns out here that f is continuous. But what about f partial with respect to y? If I look at the partial with respect to y, what would that look like?
Y to the 1/3,
Yeah, 1/3.
y minus 3.
And I'm going to subtract 1 from the bar, so it's going to be 2/3, right? Now that's a problem at 3.
Yeah, because if you get 0 there, it's...
Right, not continuous at 5. Not continuous at y equals 3. So now I want you to appreciate what this actually means. It doesn't mean that there isn't a unique solution. It just means that we don't know. So we don't know whether or not there's a unique solution. The theorem isn't an if and only if. It just says if these guys are continuous, we will have a unique solution. It doesn't tell us what's going to happen if they're not continuous. So in this case, it's not continuous. So what we would do is we'd go through and we'd actually try to find the solution. Okay, let's actually solve this. How would we find this solution?
Separable, yeah.
It's separable. So this means I can have y minus 3 to the minus 1/3 dy is going to be equal to x dx. I can integrate this. This is going to be y minus 3 to the 2/3 times 3/2. This is going to be x squared over 2 plus a constant. I would be able to solve for y. So multiply both sides by 2, divide by 3. So I get x squared over 3 plus a constant. I would take the cube of that, then take the square root, which will give me a plus or minus. Right?
Oh, yeah.
Yes.
Yeah, because you did the.
3, 2.
Yeah.
But we need to add a 3 here. Right? Because I saw it's y minus 3.
Oh, okay.
So I added a 3. Okay. So now we have that guy. Now, is that a solution? Well, for sure it's a solution. We need to find the C, find the initial, make sure the initial condition works. So, y of 3 equals 3. This means that if I plug in 3 for y, that's what I'm going to get if I get 3 for x.
C is 9 or 3.
And so C is going to be what?
9 or 3.
Right, or 3, right? So C is going to be minus 3. So turns out that y equals 3 plus or minus. And the plus or minus actually doesn't matter here because I would get it equal to 0. So I would have x squared over 3 minus 3 cubed. And this here is 2 solutions. So we don't have a unique solution in this situation. Both of those functions actually solves this differential equation, whether I take the plus or the minus. Also, here's another one. Notice here my y value is giving us 3. Something that we always try to check is there a constant function that gives the solution? And the constant function also here would obviously be y equals 3. So put y equivalent to 3, meaning it's just a horizontal line. Is that going to work? Well, if I take the derivative of that, I get 0. And if I plug in 3 over here, I get 0. So that's also a solution. I just found 3 solutions to a first order differential equation.
What does it mean to find 3 solutions to a first order differential?
The existence and uniqueness theorem fails. Well, not that it fails. We didn't have the actual conditions for it. Right? So this is just to show you, just because we're continuous and we can actually solve something doesn't mean it's going to fit the particular statement of the existence and uniqueness theorem. We have to have a lot of things falling into place. So we were not guaranteed a unique solution, and in fact, there's no unique solution. This has 3 solutions. Let's tweak this example a little bit, though. We failed continuity on the partial with respect to y. What if we didn't? So here is a situation where we didn't have the existence and uniqueness theorem backing us up. We got into trouble. what if I did something like this? dy dx equals x. Exactly the same value. So now, y of 3 is 30. Now what's going to happen? Now, f and partial with respect to y are continuous. Around 3. Right? Because if I find the partial with respect to y, I'm going to end up dividing by y minus 3 to the 2/3, but if I plug in 30, that's not going to be a problem. And if I plug in any numbers close to 30, also not going to be a problem. So we actually have both being continuous. So this means, just by tweaking that one little thing, nothing else changing, we're guaranteed a unique solution. Let's actually find it. So, separation of variables is going to bring us here, right?
Replace it 3 with 30.
Come again?
Right in front of you?
Yes. So, we do the separation of variables thing. What are we going to have happen now?
30 plus or minus square root.
So we're going to have y equals 3 plus or minus the square root of x squared over 3 plus c cubed. By separation of variables, I'm not going to repeat the steps. Now, applying the initial condition, plug in y equals 30, and plug in x equals 3. So that's going to be 3 plus c cubed. What's going to happen now is I'm going to get 27 is equal to plus or minus this. 3 plus c cubed. Now, I'm forced to choose a sign, because that is a plus 27. Which means I have to choose a positive, and this drops out, because the negative radical is not going to fit the initial condition. And now what we're going to have is 27 to the 2/3 minus 3 is equal to c. And we're going to have y equals 3 plus the radical of x squared over 3 plus 27 to the 2/3 minus 3 cubed is the solution. You can also check. Does a constant function y equals 30 solve this equation? The answer is no. Because if you plug in 30 here, you're going to get something non-zero over here, whereas the derivative is going to give you 0. So there is only one solution.
I have a question about dropping the negative sign.
Yeah.
Yes?
What if 3 plus c cubed was negative, so the cube would evaluate it to... Wait, it's the square root?
It's a square root.
Oh, okay.
Yeah, so that has to be positive. So, when the existence of uniqueness theorem fails, you have to have all these conditions. You have to have continuity in the function. You have to also have continuity of the part in the partial with respect to y of the function. Once either one of these slip up, there's no telling what you can have. You can have infinitely many solutions. You can have 3 solutions like we just had. You can have no solutions. You can have all sorts of things. But with all these conditions fulfilled, even when you ended up with a bad situation before, once you're making choices so that continuity happens where it's supposed to happen, it will automatically get rid of all other solutions except one. And in reading through the Picard's iteration method, you're going to realize why this had to be the case. It's much too complicated for me to explain in one class.
Question. I was just confused. Why did you just pick the plus sign and not the minus sign?
Because I have plus 27 over here. How is it plus 27 can equal a negative radical?
Yeah.
you grab that?
Yes. I'll probably do some examples where I graph next time, because I actually wanted to make sure I got through at least talking about the Wronskian today, and it's already been quite a while. Actually had another. Another situation. Maybe we'll talk about it next time as well. So next time I'll probably give you some more graphs where you can actually see visually what is actually going on, why you wouldn't actually have the unique solutions in some situations. But that's just a computational example for you to actually see. Once you tweak things and choose your initial values so that you get the continuity in the places that you need it, you're forced into a unique solution. And if you don't have it, well, you don't really know. It's worth mentioning that in this situation, you could have a unique solution, it's just not guaranteed. It's something you just have to figure out by going through the problem. I think this is the last thing I wrote. Okay. Let me erase this. Let us move on. Let's pick up back where we were last time. I just wanted you to start thinking about the first order existence and uniqueness theorem as well. I can give you a crash course in linear algebra to get you to understand somewhat the nth order linear case, but to teach you enough real analysis to understand the first order nonlinear case, it's actually, yeah, it's not going to work out. Last time, we saw that this differential equation, y to the nth derivative plus, whatever I call this, was it a n minus 1, y to the n minus 1 plus y dot a0 y equals 0, with y to 0 equals y0, y prime to 0 equals y to 0, all the way up to the n minus first. So we have n initial conditions, n minus 1 initial conditions equals y to the n minus 1, 0. Has a unique solution whenever the AI are continuous. Moreover, we know exactly what this solution would look like. The solution will consist of n linearly independent functions. Constant 1 times y1 is constant 2 times y2 plus constant times n. There will be n linearly independent solutions because the solutions form an n-dimensional vector space, and we know that there will be n of them because we had the n by n matrix. And so it has to be exactly n, can't be less, can't be more. And we also showed that if any two things are a solution, the sum of them is a solution and a constant times them is a solution. So we end up with the linear combination of these n guys being a solution. Okay, so now, let's talk more about satisfying the initial conditions, because in figuring this out, I never actually touched the initial conditions. Now, how do we know C1, C2, Cn can be chosen to achieve the initial conditions? Let us see. How do we figure that out? So, given that our y is the solution, so our y of t is going to be C1 y1 of t plus C2 y2 of t plus Cn yn of t. We can start to actually plug in the t naught, and so this means that C1 y1 evaluated at t naught plus C2 yt evaluated at t naught plus Cn yn evaluated at t naught will give us y naught. C1 y1 prime plus C2 y2 prime dot. We can essentially, by differentiating that equation n times, we can actually, well, n minus 1 times, we can actually get a system of equations. y1 to the n minus 1th derivative plus c2 y2 to the n minus 1st derivative plus equals y0 to the n minus 1. Now, notice here, we have n equations. And n unknowns. And the unknowns here are, in fact, don't mix them up, it's actually the c's. I want to know that I can choose coefficients that gets me those initial conditions. In theory, the y1, the y2, the y3, these will be functions that I already have found, and I can evaluate them at a certain point. So these guys are going to be constants that I know what they are. What I don't know what they are is how can I choose the coefficients so that the linear combination will create a solution. So these guys are the unknowns. But I have an n by n linear system. Which means we can think in terms of Kramer's rule. Right? The coefficient matrix is going to be the matrix of all the y's. Kramer's rule, which we spoke about last time, implies that this will have a solution. Moreover, that solution will be unique. So there will be a set of C's that I could pick that will be unique to the given initial conditions. If the determinant of the matrix of coefficients, namely the y1, y2, yn, y1 prime, y2 prime, yn prime, y1 to the n minus 1, y2 to the n minus 1, yn to the n minus 1 is non-zero. As long as I can make sure that will happen, I will be able to find a unique solution to fit any given initial condition. So I know the general form of a solution is going to be unique. It'll look like that, where no matter what method I use to figure out what the y1, y2, all the way up to yn is, it's fine, because once I find n of them that works, they're going to be the only one that works, as long as they're linearly independent. Now when it comes to whether those guys can hit any initial condition, I would require that this determinant not be zero. And this determinant is important. Muy importante. We give it a name. We like to name things that are important. Math people just, that's how they, if you like it, you put a name on it. We name it Wronskian. Because the mathematician mathematician Wronski is his last name, was instrumental in coming up with its design. So we call it the Wronski determinant or the Wronskian, affectionately. Now, what I want to do, we did a lot of things theoretically with very large systems. Let's bring it back to second order differential equations. So now that I told you how everything works way up there in n dimensions, let's bring it back to 2. Let's make sure that we actually see how this plays out in the things that we've been studying over the past 2 weeks. Back down to solving. We have an existence and uniqueness theorem. It says that the IVP, the initial value problem, y double prime plus p of t y prime plus q of t y equals g of t, where y of t naught equals y naught, y prime of t naught equals y prime naught. So I only have 2 initial conditions here. There'll be 2 arbitrary constants of integration. Will have a unique solution that is twice differentiable on any interval where the p, q, and g are continuous. Moreover, we can add to that. This solution will have the form y equals c1 y1 of t plus c2 y2 of t, where y1, y2 are linearly independent and solve the ODE. And we're just going to do a lot of things for free now, because we really did a lot of heavy lifting last class. And if the Wronskian of y1 and y2, it's called the Wronskian, you might write it as a function. So it's the Wronskian of y1 and y2. Which I've asked on like a couple quizzes now. So we finally we get to know what this is, which is y1, y2, y1 prime, y2 prime. It's just a determinant, which is this times this, y1, y2 prime, minus this times that, y2, y1 prime. And if this is not equal to 0, we can uniquely with guarantee get that the existence and uniqueness from Cramer's rule from the linear algebra. Find C1 and C2 to fit the initial conditions. Now all that stuff I told you about second order differential equations with constant coefficients 2 weeks ago, this is why we could do it. This is why it was okay for me. Let's guess the solution to the RT. Let's see if it works out. And we found 2 things, and we were fine. Why were we fine? Because there's a theorem that says if we find 2 guys that are linearly independent, those are the only solutions. Any other solution that anyone else comes up with by any other method will necessarily be a linear combination of those two. So whatever method I use to come up with them is fine. And that's why we can start with, let's try this, let's guess this, let's do that. The existence and uniqueness theorem not only gives us confidence that the answer is there, it gives us the freedom to get to the answer in any way we choose. If we see something that's nice that might seem like it work out, we're free to actually try it. And it's mathematically sound, because we pretty much has this thing that says, if we're looking at a second order linear, if I find two functions by whatever voodoo I want, and they're linearly independent, it's fine. If that voodoo consistently works, it's fine. Right? So this guarantees that we can, our methods are good enough. We don't have to look for anything else. And we have a lot of guarantees here. As long as our coefficients are continuous, we are guaranteed to find a solution that is twice differentiable, consisting of a linear combination of two functions. And provided the Wronskian of these two functions is non-zero, I'll be guaranteed to find this. And our methods always actually guarantee that the Wronskian is non-zero. And so that's why when we saw the repeated root case, we were in this, the one situation that kind of gave us a little bit of trouble was the repeated root case where we only had found one solution. So we used reduction of order to get to the other one. We realized that when multiplying by t, that actually fixes things. Now, let's maybe do that. It's worth mentioning. I don't remember the answers. Once we got repeated roots, let's say we found, say, e to the 2t by reduction of order. We found a second function, t e to the 2t. And for a second order linear differential equation with constant coefficients, it's always going to just be u at t. You don't have to do reduction of order, just multiply by t and it'll fix it. Now, how do I know that those two things are linearly independent and they would actually give me a good solution that will hit any initial condition that I want? Well, what?
C1, C2, C1e to the 2t plus C2t e to the 2t is equal to 0 only when C1, C2 are 0.
Yes, so that means they're linearly independent. But how do I know that I can actually solve any initial condition that's in my program? Well, if I look at the Wronskian of e to the 2t, t e to the 2t, that is going to be e to the 2t, find its derivative, t e to the 2t, find its derivative, and this times that, I would have e to the 4t plus 2t e to the 4t minus this 2t e to the 4t. That's going to cancel out. That's going to give us e to the 4t. Where is that 0? It's never 0. You can check, this will solve the solution. Reduction of order guaranteed it for us that that will solve the solution. Furthermore, it is going to be linearly independent because if you take out constant times that plus a constant times that, setting equal to 0, the constants would have to be 0 to get that to work out. Furthermore, taking the Wronskian of them gives me something that's non-zero on the entire real line. Those two are the solutions that I'm looking for. Well, I found another solution. I can write that as a linear combination of those two, so I don't need your solution. My solution is good enough. Right? Existence in me is there. Yeah. We're in an exclusive club. I don't care what else you can throw at me right now. These guys would solve whatever example I got where this was the thing. These two guys, y equals c1 times that plus c2 times that, is the solution. Any other solution you give me, I can write it in terms of those. Any initial conditions you give me, I can definitely solve for it. Uniquely, guaranteed. All right. What else do I want to say? Probably not much. Yes, I also want to just state a phrase that you might see. If y1, y2, yn solves an nth order ODE and the Wronskian of y1, y2, yn is not 0, we say y1, y2, yn is we call it a fundamental set of solutions. So sometimes you might see a phrase in the book or on a test, find the fundamental set of solutions. It's just this. So the individual pieces that make up the general solution when you find a linear combination. If the Wronskian is non-zero, we call them a fundamental set of solutions. So for whatever ODE that led us to this thing, it is a fundamental set of solutions, which it would. So I guess I can make something up. So y double prime minus 4y prime plus 3y equals 0. 4y equals 0 has solution y equals c1 e to the t plus c2t, c2t e to the 2t, and e to the 2t, t e to the 2t are a fundamental set of solutions. That means that these are the solutions that give you everything you want. It will solve your ODE. It will solve it in a unique way such that if anyone else comes up with any other solution by any other means, I can write it in terms of those guys. And give me any initial condition on the entire real line. I can get these guys to fit that initial condition. It's a fundamental set.
I have a question.
Yeah.
Did you already know the answer, or did you like solve it really fast and you had the ODE?
Well, I just pretended that was the answer and came up with an ODE.
Oh.
Remember, because it comes from a quadratic, right? I just wanted a quadratic that repeated root. So I just thought in my head, what is y minus 2 all squared? I wish it was more impressive than that, but it wasn't. But yeah, you want to know how I did that, don't you? No, I just thought it was x minus 2 all squared. Give me that. Because remember, once you actually do our method, it changes the second order ODE into a quadratic. We're going to do higher order. We're going to change those into nth degree polynomials, and things will start to get interesting. But for now, we're in second order, so we can just deal with the quadratics. Anything else I wanted to mention before I move on? That's open. Like last class, I went off script, so I'm kind of lost where I'm actually supposed to be. It's like, oh, I jumped around, I told this and I told that. Oh, it's this. Okay, now let's get organized again. Here is something cool. Yes, I think I want to do that. So, there are times when we need to be able to talk about the Wronskian before we actually even go through and solve the system. Because sometimes the system might actually be very difficult to solve. So let's actually talk about something that's going to help us out in that regard. So we have the Wronskian of y1, y2. We saw that that was what? y1, y2 prime minus y2, y1 prime, right?
No. Yeah, yeah.
AB minus B.
Yes, that's it. Let me ask you something. If I were to differentiate this with respect to t, what would I get?
Product.
Yeah, product rule. What would I get? y1 prime, y2 prime, plus y1, y2 double prime. Here, I would get y2 prime, y1 prime, minus y2, y1 double prime. Right? What's going to happen here? These guys would cancel. And I would have what? y1, y2 double prime minus y2, y1 double prime. Right?
That's a square.
Huh?
That's a perfect square.
No. No, these are the guys just canceled.
Yeah.
Okay, where are you going with this? Okay, hold on. I see that look on his face. Okay, why did he just show us what W prime is? Okay. It's like, yeah, I see what you did, but I'm not sure why we're talking about this.
Isn't it just another Wronskian?
No, that's the derivative of Wronskian.
Keep going. Wait,
Okay, so suppose we have.
Oh, wait, I think, wait. No, you can keep going. I'm just thinking of stuff.
Okay. Suppose we have y double prime plus p of t y prime plus q of t y equals 0. Okay? And p, q are continuous. Okay. Now, what does that mean? I'm guaranteed to be able to find a solution here. So, we know there exists solutions y1 and y2. I probably don't even know what they are right now. But I know they're there. So this means, let's go way back to the first class. What does it actually mean to be a solution? It means if I take this function, plug it into this differential equation, it makes it true. This means that y1 double prime plus p of y1 prime plus q of y1 will give me 0 when I plug it in, whatever that function is. It might not be an exponential because it depends. These don't have to be constants. They can be whatever. And if I take y2 double prime plus p of y2 prime plus q of y2, that should also give me 0. Okay. Let's call this equation 1. Call that equation 2. What?
Okay, here we go.
Okay. So let's see what happens. Something might happen. I'm just saying. I am going to actually eliminate. Let's try to eliminate something.
You creating a system with them?
Huh?
Are you creating a system with them?
Am I doing what?
Are you creating a system with these guys, or?
I just created a system.
Okay,
I
so
consider
yeah.
this as a system.
Oh, so yeah, we can subtract them from each other and do.
We can do stuff with them that we can do with systems.
Yeah.
Here's what I'm going to do. I am going to take equation 1, and I am going to multiply by minus y2. I am going to take equation 2.
I know what you're gonna do.
You don't know what I'm going to do.
I kind of
You don't know what I'm going to do.
I kind of.
You don't know what I'm about. You're gonna come on. I'm gonna do this multiply by that. Because this is what happens. So I go through, I multiply this. So that's minus y2 y1 double primes minus p y2 y1 prime minus q y1 y2 that will equal to 0. If I multiply the second one by y1, I will have y1, y2, y prime plus p of y2 prime y1 plus q of y1, y2 equals 0. Let's add these. I knew you were going to do it. Add these two, what do I get? Well, I get y1, y2 minus y2, y1. Here I would get plus p of y1, y2 prime minus y2, y1 prime. These guys would just die. Equals 0. Does that look familiar? Oh, this guy right here. Wait, what's that guy? That's not that right. What's that? How did you guys see this coming? Did you?
I thought we could do stuff like matrix operations on several differential equations. I just hadn't seen it done yet.
Oh.
So
What do I have here? This is w prime plus right times delta equals 0. I have created a first order differential equation with the Wronskian. Let's actually solve this. Now remember, nothing was assumed about my solutions. I don't even know what they look like. I just know that if I find two solutions, I can create this thing. And we know how to solve that thing, right? How do we solve that? Separable. So dw over w equals minus p. Yeah, back to square 1. ln of the Wronskian is going to be minus pt as a constant. And so the Wronskian, it turns out, of two solutions may always be expressed integral of p. Yeah, we actually don't know that p is a constant here, sorry. So this is a function. So whatever this is, it's going to be an integral. So here it's p of t, whatever that integral is. The Wronskian of two solutions is always expressible as a exponential. Now, here's something that you can notice about the exponential. This is either always 0 if c equals 0, or
Never 0.
never 0. So that kind of tells me, only in the off chance that my Wronskian does not identically give me 0, otherwise I'm going to be able to find a fundamental set of solutions to these guys on any interval where these guys are continuous, which means that this integral will exist by the fundamental theorem of calculus. That I didn't come up with it, I wish I did. But it was way before my time. A guy named Abel came up with this, and this is called Abel's theorem. And that was the proof of Abel's theorem.
Professor,
Yes?
is that exponential, is that new? From the integrated factor?
No, we didn't really need one here. Think of this as something separate entirely. We didn't need an integrated factor, it was separate. So this is called Abel's theorem. Which means, given y1, y2 solutions to a homogeneous solid, we must have the Wronskian is expressible in this form. specifically for the solid y double prime plus p of t y prime plus q of t y equals 0. And that's a theorem. Not only so in order to know how the Wronskian is going to behave, essentially, we don't even need to know how to solve the system. Integrate that and throw it in the exponential function, and whatever my Wronskian is, it's going to behave like that function. There are going to be cases where knowing how to find the Wronskian is going to be very important, and sometimes something might be really annoying to find a solution to, but having the Wronskian is going to be almost the next best thing, and this actually gives us an expression for calculating the Wronskian. So, very important theory. And if you were in a section taking a uniform final, it would actually be required for you to know how to prove this theorem. It's been a staple under departmental finance for a few years now. They always have a question, oh, prove this. How do you know the Wronskian is always 0 or never 0? Oh, because there's this Abel theorem that I can prove and I can do. Yeah, so they just always have you regurgitate that. Okay. So, spoke about existence of uniqueness theorem for first order. I told you about the Wronskian, and I told you about Abel's theorem, and I told you about a fundamental set of solutions. Okay, I think we're all caught up. If I was being good, what I just told you we would have known like 2 weeks ago. But I don't regret the detour. Yeah, so I think that actually brings us all the way up to 3.5. So,
Can we jump into going to
yeah, so I kind of hopped, skipped, and jumped around, but I covered everything we would have learned between 3.1 and 3.5. So next time we'll start 3.5. This is when we deal with a non-homogeneous case. What if you don't have a 0 on this side? Tune in next time, we'll see what we do about it.
Can we do an example of one of these? This is not a trouble.
Come again?
Can we do an example of one of these using the...
Oh, how do I know what the Wronskian? Let's use that example that we had before with the e to the 2t.
Okay.
Let's look at that original equation. What did it look like? We had y double prime plus minus 4y prime plus 4y equals 0. Let's say I didn't solve it. What would the Wronskian look like? Well, the Wronskian has to look like CE to the integral of minus 4 dt. That is going to minus, right? Because it's a minus p. So that's going to be what? CE to the 4t. And it was actually 1e to the 4t.
That's crazy.
Yeah, I could know what the Wronskian was going to do before it did it. Abel's theorem.
So could you then...
So for us, for this example, C actually happens to be 1. Yeah.
Is there a way to work backwards from that?
I was about to ask the same.
We need more information. Like, I can't just give you this and you figure it out. Like, you need more information. You need some initial condition or something else to go off of to figure out what the C is.
I was just going to say...
But I just know, whatever the Wronskian is to this, it's going to behave like an e to the 4t times some constant. Which, it behaves exactly like e to the 4t. Okay, so... we'll stop there. We'll pick up with that on Wednesday. We'll do the non-homogeneous case. What? No, no.